Kia ora, and welcome to this demo video for the Optical Bathymetry Toolkit. In this video, I'm going to show you how we can convert high-resolution aerial imagery of any waterway into a detailed and accurate digital elevation model of depth. I will walk you through the processing pipeline within our software product, including how to ensure the accuracy of our final output by using independent validation data. So the example we're going to be working through today is using real data we have collected in July 2021 of the Ashley River, or Rakahuri, which is located in North Canterbury in the South Island of Aotearoa, New Zealand. So we've surveyed approximately 8 kilometres of the river from this railway bridge here right down to the State Highway Bridge. It's approximately an 8 kilometre length, and we've actually collected that in a single day using 2 drones. So we've split it into 2 reaches. The first reach is about 5 kilometres, was collected using a DJI Phantom 4, and the second reach was flown about 3 kilometres using a Matrice 210, which was equipped with a DJI X4S camera. So both of these cameras have slightly different characteristics and therefore slightly different colour qualities. I'll just zoom in here on the transition point so you can see this data on the right hand side is slightly brighter than the data from the Matrice, and so I'm going to show you how we can account for that within our software to avoid any issues with the final DEM. So at the same time as flying the drone, we had a remote controlled jet boat in the water equipped with a depth sounder. So that depth sounder was also connected to a Trimble RTK setup, allowing us to record the water level accurately in real time also. Now what we've done is we've zigzagged that boat generally down the main braid with the intention of getting a wide range of depth and color characteristics to use for calibration data for our machine learning process. So you can see we've just zigzagged our way down. As you may be able to see in the imagery, the water is not very clear. It was fairly turbid on the day. It was a reasonably high flow. We had some shading, and it was estimated on site that there was no visibility beneath a depth of about half a metre. So once we've collected our imagery, as well as our boat data, and we've processed it through our drone processing photogrammetry software, we're currently using Agisoft Metascan. The next step is to delineate the waterway. So we've taken time to do that as accurately as we can. Again, just zooming in. We've done this using a combination of auto image recognition techniques as well as some manual processing. And you can see we've excluded a few areas which are actually very shallow pools of water, as the drone is able to accurately see through that clear water, so it didn't need to be delineated. In addition to delineating the waterway, there's 2 other inputs which I've used for the machine learning process for this job. The first is what I call a chainage raster. So I've just generated a raster which tells the software the distance down the center line of the river. So it's just starting at 0 meters at this end and going down to about 8,400 meters just beyond that bridge. Now the second input specifically for this job, because I've used 2 drones, is a split raster. So all I've done is I've generated a raster and I've assigned a value of 1 to the water surface flown with the Matrice drone, and I've assigned a value of 2 to the Phantom data. Now that just helps the software know that there's slightly different characteristics in each of these sections, and helps the machine learning to get a really accurate result. And just so we can see, the final output which we're working towards is a DEM digital elevation model of depth. Right, so we're now going to move into our software and I'll work you through the pipeline. So this is our main landing page for the software for the Optical Bathymetry Toolkit. So as you can see, there are 6 modules. Our first module is the data preparation module. So this module can be used for cleaning some input survey data if you believe there's some noise in your data set, and it's also used for extracting variables from our rasters such as our RGB pixel values to our survey data points. Our second module is our curve fitting module. So this module just is using quite basic curve fitting techniques to try and find a relationship between color and depth for our input data. Our third module is our most advanced module, which is our machine learning workflow. So we're going to be working through that in detail today. And it's basically just a very advanced workflow for finding relationships between colour and depth, and it's particularly useful when the curve fitting module is unable to find a basic relationship. Our fourth module is the apply pre-trained model. So you use that if maybe you've already run this analysis on a previous day, you've saved your model, and then you want to apply that relationship against your orthophoto. The fifth module is the option to apply a smoothing algorithm. In some circumstances, you can get a bit of noise in your final output data in the final raster of depth, and this is just a workflow to choose a smoothing algorithm to remove some of that noise. And the final module, you'll see it's actually got inactive in this version because we haven't completed our user guide 100%, but that will soon to be released and will be incorporated into the software. So that's it. So we're now going to move on and use the data preparation module. So we simply navigate to the data preparation module. Now once we're in the module, it gives us two options. Firstly, to clean and process survey data, or our second option, which we're going to use today, is to simply generate an input file by extracting our data from raster and shape files. So we have two input modes. The first mode is to use our single or multiple file input mode. So for this one here, we just simply navigate to the folder where the data is stored. And you can have it stored in multiple locations as well, and we just have to select the files which we're going to be using for the analyses. Or the other option, which I'll just show you now, if you have all of the files saved in the same folder needed for the analysis, which we have here, you can use the folder input mode. So it's nice and easy. You just select your folder and you click load file. And so then we just need to tell the software what each raster is. So the first raster has one band, so we just give that band name chainage. Then we have our split raster. Now you remember the split raster just defines which part of the orthophoto was generated by which drone. So we use two different drones for collecting this data. Then we put in our RGB bands for our orthophoto. And then for the shapefile, it asks us which columns do we wish to retain. So I'm going to retain the name because we need an ID column, and also the depth column, and I won't actually need anything else. And then we simply click extract data. It's very fast. And then we choose a save location, and I'll save that in the output data folder, and I'll go upload. And then that's done. And now we can just navigate back to our landing page. So now that we have prepared our input data, we've extracted our data into a CSV file, it is now ready for input into the machine learning workflow. So we simply enter the module and select our CSV file, and then we load our data. So the software just displays the first 5 lines of that CSV file, just so that we can be sure that we have selected the correct file. And then we need to tell the software what each column within our CSV file is. So the software needs an ID field, so we're using our name, and then the easting and the northing is for X and Y. Then simply we have our RGB, our red, green and our blue pixel values. We're also going to load in our chainage as well as our split rasters. And then the final column which we're inputting is our target column, or our target variable which we're solving for, which in this case is depth. We click proceed, and then it asks us to choose one or more color space to work with. So most traditionally, people are familiar with RGB, your red, green and blue pixel values, but we can also transform your RGB values into various different color spaces, one of which is HSV. And it's just a different way of looking at our color values. So I'm actually going to use both color spaces, both RGB and HSV, for this demo video. Now it asks us if our aggregate distance has been calculated. That's just the distance between points. It's very useful for plotting profile plots, for example, to have a distance column. So I'm just going to click no, it calculates it for us, and then we enter the machine learning pipeline. So again, it just shows us a sample of the values which are being used. We've got our RGB, HSV, our chainage and our split. There are independent features, and then for our dependent or target feature, it shows us some samples of the depth values. Now we want to move on and we simply click Apply Feature Engineering. So what the software is doing here, it's actually using domain knowledge to aggregate, transform, and create a wide number of features using a range of different data mining techniques. So once it's created these new features, the program's then able to use a range of different methods, traditional and embedded methods, to select only the features which are going to contribute most to the prediction of the target variable. And this most accurately represents the underlying structure of the data. So this is really important, and it actually significantly improves the performance of the machine learning algorithms in learning and finding patterns within the data and their relationships to the target variable. So this stage for this data set on my laptop takes about 10 minutes. So I'm just going to pause the video here, and then we'll pick back up once it's finished this part of the workflow. Okay, so now that the feature engineering process is completed, we can now move on to telling the software which machine learning algorithm we wish to use with this dataset. So there's 5 different techniques we can select. If you have run the software before over a similar dataset, you may have a feeling for which technique will give the best results, or alternatively, you can simply run all 5 techniques in parallel, which is what we're going to do now. Our next step is to select a preferred mode for training and validation split strategy. So you've got the option to input an external file to load a previously generated training and validation split value and indice, or what we're going to use now is we're going to generate a new training validation split value. So there's 4 different options here. The first option allows you to choose the percentage of data points. For example, you may choose 80% of the data for training, and 20% of that data will be withheld for independent validation. And then the software will randomly split your dataset into training and validation datasets. The second option is similar in terms of you choose your percentage of data points to be used for training, but rather than selecting independent points, it will select spatially connected groups of continuous data to use for validation. Now, that's really nice. One of the advantages of this is that you're able to plot long section profiles of your validation points against your survey data. So it allows for a visual check of the data, not only using validation metrics. Another option is to upload your own validation CSV. Maybe you've got some independent validation data which you would like to test the machine learning against, or if you're really confident, you could ignore validation completely and move to use 100% of the data for machine learning. Generally, I would always like to have some validation data. So for this example, I'm going to use our second example, and we're going to be using grouped data sets for our validation. So I move on to here. I simply input the percentage, which I wish to use for training. So here I'm going to choose 90%, and I select go. And now what the software is doing is it's running off and it's putting those data sets through our machine learning pipelines. And it takes a few minutes, so I'm just going to pause the video here, and then once it's completed that, we'll start comparing the outputs together. So the software has now run each of those machine learning algorithms over the input dataset, and we can now inspect the outputs. So the first thing which we can look at is the model training performance metrics. So this first table gives us the metrics for our training data. So we output 5 different metrics. The first one is root mean squared error, or RMSE. So as you can see, Technique 2 and Technique 3 have probably performed the best. We have our mean absolute error, so it's performed really well on this. For Technique 2, we've got a mean absolute error of 3 centimeters or 7 centimeters for Technique 3. We have a Pearson correlation coefficient, or R-squared goodness of fit. Now again, for Technique 2 and Technique 3, we've got really high values of 0.99 almost and 0.95. Maximum residual error, and explain variance score. So there's always, this sort of shows you the outliers. So we've got 1 or 2 significant outliers at least within those data sets. And now probably the critical one we want to look at is the second table, which is our performance metrics on the validation data. So you can see again, Technique 2 and Technique 3 have performed the best. The metrics are not quite as good as the training data, which is to be expected, but we've got a mean absolute error of in the order of 10 centimeters, which is really good. And we've got really high Pearson correlation coefficient of 0.87 for both of Techniques 2 and Technique 3. Again, we've got a couple of outliers, which we would expect. We're never going to get a perfect result. And potentially there's noise in the data set anyway. And our validation explained variance score giving reasonable values, particularly for these two techniques. Here's some sample predictions for each of the, so here's our depth. We can see a depth of 0.2. It's predicting 0.3. This one was 0.18 and it's predicting 0.5 for Technique 3, but Technique 2 has predicted that one really well. And so now we've got some options. We can save the training and validation split file. So maybe we want to rerun this analysis with some different parameters and we want to use the same training and validation split. We can save that as a CSV file. We can also just save the training and validation CSV file, so that's the actual results. Maybe we want to plot them ourselves within a software such as Excel. And we can also save these training and validation statistic text files. Alternatively, we can just copy and paste any of the data within here and copy that directly into whatever software package we're using. So the next step is to actually visualize these outputs. So the first plots I look at is just plots of actual versus predicted depth against the raw data. So we can move through and compare the outputs of each technique. So you remember Technique 1 didn't give as good results in the metric tables, but Technique 2 and Technique 3 actually gave really good results. And just showing you here, Technique 4, Technique 5. So we'll come back to Technique 2. So you can see we've missed a few of these points, but overall, if we zoom in on some of these groups, you can see that it's giving a really good fit. Now, this is not purely validation data. This is a mix of the training and validation data sets. Now, another way we can visualize that data is to sort it via depth. Now, I really like that because then you can see, is it picking up most of the points? Are there any trends in it? Is it missing the low points or is it missing the deep points? So again, you can just zoom through the different data sets. Technique 3, we've got it appears to be a little bit more variation around that mean. And then Technique 4, for example, hasn't really worked very well. Technique 1 probably hasn't worked very well, but Technique 2, I think, is probably giving us our best fit. So I'll move on from here, and now we want to look at our validation profiles. So you remember we selected grouped data to use as the validation profile. So you can see here these orange points are the groups of data which the software has withheld to use as independent validation data. So now we can visualize each of these profiles. So moving down here, so it's selected 10 different groups of data, and we can just move through. How about we select the odd numbers? So you can just see most of that again is within 100 to 150 mils. Let's go to group 5. You can see that's got a really good fit. We've missed 1 point here, but overall it's got an excellent fit. Let's go to group 7. Again, beautiful fit. One noisy point here. That can be cleaned out using our smoothing algorithm at the end if we wish to. Let's have a look at group 9. Again, we've got a really good point, so we're picking up all the way down from 0.4 up to 1, back down. So it's really picking up the variation, and again, there's the odd noisy point, but overall the trend is really good. So if I was doing this job, I'd be really happy with that output. And then I would move on to the next part of the analysis. So if we wish to save these validation plots as a PDF file, we can just click this and we can save that, so we can put that straight into our report if we wish. Or earlier we had the option to save our validation data sets as a CSV file, so we could also plot that ourselves within Excel if we wished. And again, the option to save the model file, so that's if you don't want to go ahead with the predicting against all the full data points now, you can save this model and you can come back to it later. But for now, we're going to move on to proceeding to the full data predictions. So that's really straightforward. We can select a preferred mode of input. Either we have a CSV file of data points to predict against, or most likely what you're going to have are TIFF files with your orthophoto. So we want to choose our RGB raster first. So now we're just going to use the same data which we used for the input data. So here's my water surface mosaic, which is my RGB raster. We need our chainage raster. We need our split raster. And that should be everything. And we go load file. Now we need to tell it which bands we're predicting against. So we've got RGB, chainage, and split. And then it asks us which resolution. So my input orthophoto is a 0.2 meter pixel resolution, or a GSD. If we want to resample that to a coarser resolution such as 1 meter, we could do that now, but I'm happy to proceed with a 0.2 meter resolution, so I simply click proceed. It will then ask us again just to define these bands. So RGB, sorry, chainage went first, and then split. And then we have to tell it which machine learning model we wish to use. So I think Technique 2 gave the best results, and then we simply hit predict. Right, so this is the slowest stage of the process because it's now applying those outputs to every single pixel within that orthophoto. So we can just leave that run, and I'll pause the video and then we'll have a look at the results shortly. Right, so the software has now completed its predictions for the full dataset, and it just gives a couple of examples here of our predicted values for those eastings and northings. And then, yeah, it's as simple as saving the output to file. So we can choose a location, and I'm going to put output data, upload, and it's saved the TIFF file to that final location. So here we can see our output data folder with our predictions technique2.tiff file. So let's just bring that file into ArcGIS so that we can visualize it. We'll generate pyramids so that it displays nice and quickly. And by default it comes out sort of grayscale. So personally I like looking at these rasters in a blue shading, but that's up to individual preference. And now we can see our result over the full, I think it's 7.7 kilometers. So we can just zoom in on our final results, and you can see that we get quite a nice looking natural profile. So it not only validates well, obviously, to our independent validation data, but visually, we get a nice visual validation as well. So just zooming along. Having a look at the results. So personally, I'm quite happy with that. So if we just turn that off again so you can see what's underneath. So you can see there's quite a bit of shade here, but it hasn't appeared to have impacted the results significantly. There's no sudden changes in depth where the shade was. Zooming along, we can see some areas. For example, this area looks a bit strange to me. There appears to be quite a uniform deep area here. So let's just zoom in here and see what's going on. Let's just see if it makes any sense. So just turning that off, and it actually looks like there's quite a uniform channel through here, which has likely been created through some sort of gravel extraction operations as my hunch. So yeah, there appears to have been some sort of artificial barrier pushed up here, and the braid has just broken through that barrier, and the water's started flowing through what was an area for gravel extraction. So hence the uniform shape of that deep pool through there. So I'm happy that seems to be realistic. And just so you know, like these areas here, very shallow water. We haven't spent the time in delineating every area of shallow water, so it just hasn't been used in the machine learning process. So that's our final results. So I'm really happy with this, and would be happy to use this for hydraulic modeling or some sort of volume estimation processes. So I hope you found this demo video to be useful. If you have any queries at all in regards to the software, how it works, or if you would like information on pricing, or to receive a 7-day free trial license so that you can trial the software with your own datasets, please get in contact via email on software@landriversea.com. We really look forward to hearing from you soon, and thank you again for watching this video.